Today there will be a theoretical class, maximum. Actually, we have to take some theoretical classes. I need to make a base so that if I speak some mathematical terms with you guys, you should understand what is meaning by that or what I mean to be say about that mathematical term. So I understand that some of you may feel that we are not doing so many questions. Definitely, we will do questions. Actually, after all, we have to perform the questions only. But before that, we have to understand what is the question, and to understand the questions, we need to make a base that that will enhance the capacity to tackle your questions. Okay. So earlier, if you have any doubt in the previous classes or if you have any questions regarding anything, that's just tell me now. We can do that as well. But one thing I would like to suggest that whatever notes I am sending, so please read it. It's not something that you are going to use it in your this exam only. Wherever you will go, the theory, the definitions is not going to change. And and just because you understand the basic concept, you will able to apply it anywhere, and it will be long term sustained with you. Okay. So I prefer that you should have a better understanding of mathematics rather than cramming because it's totally going to be beneficial for long time. Mm, okay, so independence we have done so far. Independence of two events we have so far done. This is this you know already that this is our probability space. Our probability space. This is our probability space, and this is the sample space. This is the event space, and this is the probability function we defined on this event space. And if A and B belongs to the script F, then if the probability of A intersection B is probability of A multi probability of B, then we define that A and B are independent events. For example, if I say if I roll a standard six-sided die twice, or I can say two dice I took that are six-sided and I rolled them, then what will be the sample space? Sample space will be ij ij that belongs to 1, 2, 3, 4. I think that's a very basic example I'm giving you. If I say that, let's say event when this is an event such that I is old, that I is old, and that B event, let's say that A comma B such that I plus B is equal to 4. Okay, so you can see that let's take something that C is also an event such that I comma J and J is okay. So when I is odd and J can be any number, then you can see that A will have what kind of that some other color that in the A what will be the favorable cases when I is odd it means one one two and 1 6. Two will not come because two is the even number and similarly three will come, five will come, and these will be the event case. And if I see B means I plus J should be 4. So then 1, 3 is the possibility, 2 is the possibility, 3, 1 is the possibility. Okay, so I hope I have covered all the favorable cases for event B. And for event C, J is 2. You just have to keep J equal to 2. It means 1, 2, 2, 2, and 2, 6. For J, you have to keep 2, right? So then 6 will be your order. Okay, so this will be 6. Okay. So you from here you can see that how many favorable places in A. This is 6, 6, 6, 18. Then if I say that here I'm writing here, no, here I'm writing here that cardinality of A is 6, 6, 6, 6, 18, and cardinality of B is 3. And cardinality means potential of the set. It means the number of elements in the set is the cardinality of that set. And you see there are 6 number of elements. So I'm just writing it. If I say A intersection B, okay, A intersection B, it will come. You can say that what are the common uh, favorable cases in A and B. That 1, 3 is there, 3, 1 is there. So only 2, 1, 3, 3, 1. So if I say cardinality of A intersection B, that is only 2. If I say cardinality of B intersection C, so B is this event, C is this event. So only possible or the common case is only 2, 2. So cardinality of B intersection C is 1. Similarly, cardinality of A intersection C. So you can see that A is this event, C is this event. So 1, 2, 2, 2, 3, 2. So here will be 3, 2, 4, 2, and this will be 5. So this number and this number will be the favorable cases. So it will be. So we have calculated the now let's see simple probability. What is probability of A? Total number of favorable cases is 18 upon 36 is the total. Probability of B is simply, you can say that is 3 upon 36, and probability of C is 6 by 36. I am just writing that I'm using that simple definition. Actually, axiomatic definition and the simple definition is the same. And when we have finite sample space, so axiomatic definition and that definition we used to do in earlier classes is the same. When we have sample space finite, when it comes to be infinite, then there are some differences comes to arise. Probability of A intersection B, A intersection B is 2, and the probability is this. And probability of B intersection C, that is 1 upon 36, and A intersection C is that is 3 upon 36. I hope this is the right statistics of the numbers I am writing. So you can see that what is the probability? Can I write it as probability of A multi probability of B? So this is the question. What is the probability of A? That A is 18 by 36 and probability of B is 3 by 36. So you can see that this is by 2. This the same color. That is 3. 3. Okay, 3 we can cancel by 12. So this is 1 by 24. So this is not equal. So this is not equal. So we can say from here we conclude that A and B are not independent. A and B are not independent. Similarly, You can check that what is the probability of B and probability of C. That is the question. The probability of B 3 by 36 and probability of C is 6 by 36. Two. So that is just a 72. That is also not equal. So this is not independent. So in section C, that probability of A, C, 36. Probability of C is what? So this is 2, 3. So this is 3 by 36. So you can see, you can clearly see that this probability is coming to be 3 by 36, and this is also 3 by 36. So probability of intersection C is coming to be probability of A, probability of C. What is this implies that A and A and C is independent. So I hope this clears the definition of independence. Now let's see another definition that is quite interesting and useful in the upcoming concepts. That is mutually independence of a collection of events. Mutually independence of a collection of events. Okay. This is mutually. Okay. Mutually independence. What is mean by mutually in pairwise or in the independence definition of pairwise? What we were doing, we have a collection of events. We were picking any event, and we were saying that probability of their intersection equals the probability of product of their individual. Then we would say that it is the independent event, or you can say pairwise independent. Now in mutually, whatever the number you take, whatever the number of events you take from a collection, whenever you are going to multiply them, that will be equal to the probability of their intersection. It means, let me write, suppose if Pi, okay, so I belongs to next number, belongs to index is collection of events. Then if probability of intersection of Pi, let me take it as N. Okay. That is equal to probability of E1, probability of E2 multiply. I'm just multiplying. I'm just generalizing the definition of pairwise independent to any arbitrary collection. And in arbitrary collection, I mean to say that it's a countable, infinite maximum. It's not uncountable. Okay. So in complex notation, I write it as, this is the definition. This is important mathematical, term. So you can say that no. You can see that mutually independence. This implies in pairwise. Independence, it means that if you have a collection of events, then if it is mutually independent, then by definition, if you take any two events from this will satisfy the definition of independence, pairwise independence. It's obvious from the definition, but the converse is not true. If you have a collection of event and you take any pair of the event that is independent, that you cannot say that the whole collection is independent, because in the collection, if you have a collection, you want to define it as mutually independent, then you have to take each subset of it that should satisfy this. And in pairwise, we only take two events from the collection. So I can say he was mostly he was, this is important. Okay, see some let's see some example. Good example. Suppose you have a 1, 2, 3, 4. This is the sample space. If you take an event, so what is the mean of event? So suppose you have a die that is written 1, 2, 3, 4, not a six-sided die. You see that 1, 2 is this, this is 1, 3. Let me take this B and this C. Let me take 1. Let me take B as 2, 3, 4. Let me take 2, 3, 4. Let's see if it should work. Then you can see that probability of A is 2 by 4. Favorable cases is 2 and total is 4. So 1 by 2. Similarly, probability of B, probability of C, and probability of D is 3 by 4. A intersection B. This is A intersection B. Coming to, you can say that only one is coming in the intersection. Okay. This is 1 by 4. And probability of B intersection C is also 1 by 4. Probability of A intersection C, that is also 1 by 4. And you can easily see that you can write it as probability of A, probability of B, and this as probability of B, probability of C, and this as probability of A, probability of C. So you can easily see that this A, B, C satisfying uh, the condition of pairwise independence. Now let's see that probability of A intersection B intersection C is what is in the intersection A B C, that is 1. One is 1 by 4. Can we write it as probability of A, probability of B, probability of C? Let's try to write it. What is the probability of A? That is 1 by 2. Probability of B 1 by 2. 1 by 2, that is 1 by 8. So you can see that this is not equal. This is not equal. So note is, if you take as collection of the events A, B, C, then S is pairwise independent. Pairwise independent, but mutually. So this is important just to keep remember. Okay, this is not in the notes actually, but still you can easily remember. It's very easy to remember. And you can see that's just a observation. If omega, the cardinality of omega is n. If you want to check that let's say S prime is any. Okay, so let me make this so that it's just not. What is this? If there is a collection, S is a collection, S is a collection of events, and you want to check that whether S is a mutually independent or not, or you want to check that S is a pairwise independent or not. To check, say that cardinality of S is okay. To check pairwise independence, actually how many operations you have to perform, that in the collection you have to pick every two pair and you have to check that this is satisfies the definition of that independence or not. Then it means that you have to see that these are the numbers of operations. These are the numbers of operations. But if you want to check that mutually independence, that we want to check that this is mutually independence, so then this is the total number of operations you have to check. And so this is K. Okay, this is K. Just verify from your side that these are very far, greater number than this. To just check that in mutually independence, you have to check more number of operations you have to apply. This kinds of question may come, but it's a very basic observation. And mutually independence and pairwise independence we have done. Mm. So now let's move to our most important aspects of our statistics that we are going to do. Uh, Function I have already told you, and I assume that everybody knows what is the function. Function have a domain. Function have a codomain. A set function, a function whose domain is the collection of set. And what is the collection of set we are dealing with? That is event space. Script F we are using as a collection of events. That is collection of sets as well. If I defined as a x, I just defined a function from omega to r. Huh? Okay, let me give you an example that if you flip a coin, head or tail will come, and if you are in a situation where if head comes, then you will get a 1 rupees, and if tail comes, you lose 1 rupees. Uh, so it means that say like just example that if omega have head and tail, and in real number, and that x you are denoting by 1 and xl is -1. So obviously you can see that this is defining a function. This is defining a function indeed. Just example. Okay, so example one. Let me take an example another that that you suppose you are flipping a coin again, and you flip the coin again and again until heads come. Until heads come. Okay, so what will be the sample space in this case? It is quite possible head comes on the first flipping, or first tail come then head come. I hope you understanding that that's quite possible. If you flip a coin, tail come. If you flip a coin, tail. If you flip a coin, then head come, and you terminate the experiment. And you goes on. And what is the sample space? Sample space is the collection of all the possibilities. And there is quite possibility that you flip a coin, 15 times tails come, then at the 16 head comes. That is quite possible. 14 times tail come, and 15 time had come, then it means that what are the possibilities? That it may be possible that tal come, then had come, or maybe tal come, and had come, and so on. It will go on. It will go on as much as you can assume. Uh, so, so if I define a function, say, let me define a function from omega to r. What is the omega? It means x have obviously a set or some a belong to this omega. Uh, this is a domain. This is codomain. Number of heads. Sorry, number of tails. Number of tails you can define, or you can define in as just for better understanding. Number of trials. Number of trials get the head. Number of trials get the head. Huh? So what do you see? It's this basic observation. Okay, so what is the basic observation? That image x of Okay, so this I am taking. This is the second example. What is the image of head? That is one. What is the image of tail head? That is two. It means two trials we required for this outcome. For this outcome, we required three trials. Tail head. It means we can define a function. Then this is mapping for four, and this is a quite reasonable function that satisfies the definition of function. So in the similar fashion, okay. So let's see what is the pre-image. Okay. So if R is the codomain, then every set can have pre-image. Okay, so it's quite possible it is not a one-one-onto function. In many cases, it is not one-one-onto function. So it's just a function that I am defining from omega to R. So it's in my hand whether it is one-one-onto or it is on the demand of the requirement. Okay, so let's see that what is mean by X inverse. Let me define on the mean that if X is a omega to R function, then what is X inverse of A? Okay, so this is the collection of all the events such that X omega belongs to A. What is mean by that? That if you have a collection, this is omega, and this is R, this is zero, and this is the set. This is mapping to say this point, this mapping to this point, mapping to this point. Say if you want to take the this is the set A. This is set A. Then what is the X inverse A by definition? If we say that it is a collection of all the omega whose image is belong to this, so let me say it as alpha 1, this is alpha 2, this is alpha 3, then this is alpha 4. Then in this collection, the inverse image is only this. Everything else has inverse image phi. As you know that if the function is not on to the events which in the codomain which do not have image that have the inverse image as empty set. So this will be the alpha 1, alpha 2. Okay. I feel that it's more the mathematical way to teach, but okay, just to make a better understanding, we can do it. Okay, in the set of A, this is A we have taken, and A can be any set, this can be the set. Why this can be the set? Because A is a subset of real line, so this can be any set. So for this, and uh, it can be this set as well, minus infinity to X open. A can be this, you know, 1, 2, 3 discrete set, and it means it's just a subset. This is just a subset of this. So if I am defining the function, you can observe some properties. What are the properties? If this is omega is so X is a function from omega to R, what is the inverse image of R? That means X inverse of minus infinity to minus infinity. That is by definition we have taken that. This is the collection of all the omega belongs to this script as such that this belongs to minus infinity to plus infinity. And you can see that this is the codomain, this is the range. Oh, no, it's a codomain of this function. Then what are the image? What are the elements that is mapping on this whole R? That is totally, it's completely, you can see this is whole R. So you can see that this is a point. And similarly, you can see that inverse image of phi. This is phi of R. That is mapping. That's inverse image is phi. That is phi of omega. Okay, so empty set always maps on the empty set. That's just the observation from the function point of view. Hmm? And, and quite reasonable. You have to verify it from your end that if A and B are subset of R, and if A intersection B is pi. A intersection B is pi. Then X inverse of A intersection B, inverse image of intersection B is this. This is a also property from the function that intersection preserve. There you should remember that what are the properties that preserve under when we see the inverse image of any set from the codomain in a function. And the final one property is okay. So if this is a this is a collection of an AI, where AI you have to assume that this AI, okay, let me write here first that I am able to write it as an AI where AI belongs to F. Okay, AI belongs to F, or these are the subset of omega, that is the same thing. Okay, that is here it is working as a element, here it is working as subset. So you must understand what is the difference between these two. Okay, so now I hope this is clear to everybody. If it is not clear, I'm sending the notes for this. So this is this is very crucial, and it's a very important part that we have to understand this. And I'm sending the notes with that has quite reasonable examples as well. Since we don't have that much time to discuss all the examples and go in very detail, because we have to cover a huge syllabus before your exam, that so that we ultimate goal we have to solve the questions, and just to solve the questions we must have to make some days, and it totally depend on your work. It totally depend on your work, that how you do it. Okay. Introduction, I'm covering the introduction. See if you have any doubt, whatever doubt you have in the concept we are going through, you just ask me. We'll try to solve it. Okay. And now let's do a what is random variable. Okay. Let's say that let omega fp be a probability space. So then x from omega to r is a random variable. Okay, let me keep it as if x is a function. X is a function, and what is f? F is power set. This is power set of omega. Okay, x is a random variable. You just have to define a function from omega to r, whichever function you just define. I hope you understand the basic definition of function. What is mean by function? That you just have to take the input, that you have to take a one point from the domain. You just have to put on a member of real line and forget that now. And you just keep note, but forget about that now. You just pick some another. You just define that image of that point to any real number. Explicitly say you can define the same image as well. So this will define a random variable, but take care that this event space is the power set of omega. That is that is cardinality of 2 to the power omega, 2 to the power. This is the cardinality of this is a cardinality. So this will be a random variable. And if you want some clear definition, that is generalized definition. Generalized definition is that uh, that no if script f is a subset of power set of omega, uh, then x is a random variable if for all a subset of r, x inverse a is event of omega. That's it. That's it. Just a notation. But This notation you don't have to go. Okay, no need to go this definition. I don't feel that this kinds of generalized definition they are going to ask, because it's required, some time. It's required some time to understand. It's a very easy. Let me tell you clear that this is very easy, but the results we discuss on just this, generalized event space, that maybe some you have a complexity. But just to understand the definition and the basic results, whatever we are going to do, if you want to do those results on the basis of this definition, that is also very very easy. But there is no hurdle. We are going to use f as a power set of omega. That will make our work very easy. No need to be, any kind of hodgepodge. So okay, so you can see that we have omega here, f here, p here. So we just have used this omega, and this is a set of real number, and this f. We didn't have used this p. Probability we didn't use. So in the definition of random variable, we are not using anywhere the definition or the notion of probability. So to define a random variable, we don't require probability at up till this moment. Now we are going to define the probability space. Now we are going to define the probability space. So I hope you remember what is the probability. That probability is a function. So uh, probability is a function for that is called f, right? Script f to 0 1. And I assume that three axioms you know what is the probability. And x we are defining from, so what is the x? X, that is a random variable. X is a random variable that I am defining from omega to. So let me see that probability of this. Okay. This is a function. What is the mean by this? This set is a R, no? And this is the even space, right? This is the even space. So this will be the, so if I say that you will see that x inverse, whenever I say that this is defined only when A is a subset of R, and or I can say A is belongs to power set of R. Here it is working as an element. Take care. Here it is working as an subset of the R, and here it is working as an element. Okay. So this is a power set of R. Huh? It means A belongs to the script B. The script B is the power set of R. I will define. So so just try to convince yourself that the T O X inverse is a function from B. B is what? Power set of R. This 0 0. What it means that P of X inverse, that is of A. What is mean by P X inverse of A? Huh? So X inverse of A is what? So this is a X inverse of A is from B to this omega. Huh? This omega. So this is the uh, so this belongs to, okay. So you can see that this set that is belongs from that omega. And what is the P? P is that image of the power set of omega. That P is subset for omega. So simply you can say this is a subset. So this is a subset. This is subset of this. And easily you can say that this belongs to this set. This set belongs to F, script F. So 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 this P as the input from the F. So this is well defined. This is, you can say this is well defined. So I am just using the definition, or the definition of P and definition of X. That is very very simple, and you have to understand this if you want to do those questions that is coming in your exam. I understand that those questions are very easy. That will be easy to handle. But if you don't know the notation, don't know the meaning of the term they are using, definitely uh, difference differences will start to occur. So you have to understand the notation of what is p and what is x, and this is known as induced probability space. This is known as induced probability space. Okay. So up till now, if you have understanding the basic till now, it means you have covered you have a good jump to the success. Now it's going to be very easy because we just have to use the notations, and on the basis of the theory we have developed up till now, we are going to use that only. Okay. Just to make the clarify some little more examples, that let me give some examples that how induced probability space that we are going to use it, and then today we will discuss a basic definition of CDF, that is cumulative distribution function. Then we will end of this lecture, and from tomorrow we are going to discuss what is the demand of our course. Okay, so we have done an example, right? Say omega is this, head, head, tail, head, tail. You understand that what is experiment? I am flipping 2 points at a time, or I am flipping 1 point twice. Then if I define probability, what is the probability? Probability is a function of that omega. Probability is a function from script f to close interval 0 1. If I define probability head, that is understood. Okay, what is the probability of head? That is 1/4. Tail is 1/4. Every is equally likely probability. So I'm not writing it, and okay. So what is, let me take it as x probability I have defined. X let me take as this, and what is x? X is x x say a is number of heads, in a. Uh, Number of heads. It means what? It means that x head, that is mapping on 2, x head tail, that is mapping on 1, because number of heads is 1, and tail head, that is also is 1, and x tail, that is 0. Okay, quite reasonable. So see that probability of x of inverse of a. Huh? Let me see. So you can see that probability. Let me define. P of x inverse is a function from power set of R. Just to make the notion convenient, I'm not writing it script B. Further, I will do script B. It's a power set of R to close interval 0 1. So if uh, it's a power set of R, so so if x is belonging from minus infinity to 0 open, huh? So here it is what? Here it is. So if this is belong to this, then this omega belongs to this omega belongs to it means this is a collection of omega belong to this, such that x omega is belonging from x belonging from minus infinity to 0. So you can see which are the omegas whose image is minus infinity to 0. That is totally empty. That is totally empty. That is totally empty. So P you have to use that P is going to, that probability of phi is 0. We have seen when x belongs to minus infinity to 0. So Similarly, for the probability of that those omega where x omega is belonging from say closed interval 0 and open one, you can see it. Huh? That means that probability of what are the values when this omega is 0, that is only say t, that is 1 by 4. It means what is the value of x? X is from 0 to this 1. Similarly, whenever you will see that probability of those omega where x omega will belong to closed interval 1, 1 to open to, so open to, it means this 1 1 is coming, then probability of head head tail, because when we are including head tail head, that is 2 by 4 favorable cases of only 50 possibility. When x is, this is equality, where it is not equality. This is 1 and this is 2. And what is the probability of omega such that x omega belongs to close interval 2 to open infinity, that is probability of head. That is 1 by 4 when x that is less than 2. 2 and okay. So this is the probability mass function. Or let me clear it. Let me write it clearly. So probability of x inverse a, that is coming to the 0 when x is less than 0 and minus infinity, and 1 by 4 x less than 0 and 2 by 4 is for say 1 by 2, that is quite reasonable, and if x greater than 2, that probability is 1 by 4. That's just a function, I'm defining it. Okay, so I understand, I feel that I'm able to teach well, that you are understanding the things, but still you have to go, whenever you go at home, you have to try it with your hand. Okay, with your hand you have to try to just make the confidence in it. And okay, so now on the basis of the question we have done, I just to make clear what is the probability induced probability space p o x inverse a, I gave the example. Now if I take a to be minus infinity to x, that's the next definition is we have to understand. If I define, let me see, if omega fp, the probability space, uh, x random variable p of x inverse minus infinity to x is known as CDF. Huh? CDF. You have heard this term before. Cumulative distribution function. That you have heard cumulative distribution function. It means what is this? That is the probability of, if you see that here the set A is what? That omega belongs to that omega, that x omega that belongs to minus infinity to x. So this is the definition of that probability. Says if I see the last example, yeah, just note it that if I see last example, huh? I hope you remember it. If p of x inverse minus infinity to x, huh? You just try to relate when x is less than 0, right? x is less than 0, that is coming to be 0. And when x is coming to be, 0 less than 1. Okay, so no, you have, what's the definition? You cannot have lower bound, just have a upper bound. This is upper bound, only upper bound is have, and lower bound is minus infinity. X is less than 1, then it will come to be 1 by 4. If x is less than 2, if this is less than 2, then what are the possible favorable cases here? That when x is less than 1, then you are actually checking the probability of omega belongs to those omega, that x omega belongs to minus infinity to any x, say uh, any x less than, that is totally less than 1. So this is it's something like this. It means which are those omega whose image lying in between minus infinity to 1. That is only that one, that is only telltale. Only telltale, because 1 is not included. Similarly, when x is less than 2, which are the numbers you are including, here it is 2 only coming. So you just have to write it as 2. So here just write 2. So you see that 0 is coming, 1 is coming, but 2 is not coming. What are the possible cases when that random variable giving this value 0? That is telltale. And when head, one value is giving, when head can tell head. These values are coming. So these are the three favorable cases. So this is coming to be 3 by 4. And if x is greater than 2, so you can see that when greater than 2, it means some alpha that is greater than 2. It means that that is covering the possibility 0, 1, 2. And these are the only possible values that x was taking. So everything is coming. It means there are total favorable cases are 4. 4 by 4 is 1. So this is the CDF. This is the CDF of that random variable that we were using it. Or moreover, if I test this, this will not harm. No, this will not harm anything. You can see that. So this we can not write here. So let's not write it. Let's not write it. It's not a time to make it higher. Okay, so this is the CDF of that random variable we have earlier defined. No doubt we have to understand the notion of CDF a little bit more. Okay. So today we are going to do this. I understand this is the whole theory class we have done, but we have to do it. But some days we have to spend our time on theory and keep it clear. Keep it clear time to time, because when we will do question, we will frequently use this all the things we are doing now. So things and the question will be very easy when we will apply this basic definition, because I don't know whosoever is setting the questions, but whosoever is setting, definitely he knows these definitions, and he is going to set questions on the basis of this definition only, because there is no other way. There is no other way to make it. Okay, so we will do some tomorrow. We will do some more, on the things, and we have holidays previously 2 or 3 days that we will cover in or 22 to 29 in the coming days, that we will cover it. And if you have a question now, then please ask, or otherwise we can.
Sir, will you take some questions regarding this topic which you taught today from the question paper?
Now we will not take. Actually, let me complete. Tomorrow we'll going to take the question. Tomorrow we have a question class. Today we
Okay,
don't
sir.
have. Today you just try to complete the theory. I will send you the theory and keep it here. Okay. This theory has so many questions and examples. It's totally have examples, but this is going to help. But questions we have to solve in our exams. Okay.
Okay, sir. Thank you.
Okay. Anything? Anybody else? Okay. So let's stop today. Okay then. Goodbye.